Hello everyone and welcome back again to another video on calculus. Last time we had an introduction to integrals, and in this video we'll continue with integration. We'll learn some basic rules concerning indefinite and definite integrals. And we will also cover the reverse power rule for integration. So first we have some theory here on this page, and then after that we'll apply it on these exercises which I've made. There's a total of 14. So let's get started. First of all, we have these general rules. If we have an integral of a function multiplied by a constant k, so this number can be 2 or 3 or any number really, as long as it's independent of x and it really is just a number, then we can take it outside of the integral like that and have the integral in this form, and the equality is preserved. And here we have a multiplication. So we just take the constant out and then integrate the function by itself with respect to x. Remember, this only works if k is indeed a constant. So the next rule is about the linearity of integrals. If we have the integral of a sum of two functions, f and g, of the same variable x, of course, then we can do what's called splitting the integral. So this is equal to the integral of f of x dx plus the integral of g of x dx. So here the equality is again preserved. And this is also true for definite integrals. We'll skip the reverse power rule for a second. If you have definite integrals with boundaries, a and b, whatever they are, you can still take the constant out, as shown here, and just get that constant times the integral of the function itself. Now same for addition. Just like before, you can split the integral, as shown here. You just have to be careful to keep the boundaries the same everywhere. Okay, so a and b, a and b, and a and b. Let's go back to the reverse power rule now. We learned for differentiation that if we have the derivative with respect to x of x to the power of n, that would be equal to n times x to the power of n minus 1. Okay, remember that rule? We have a similar one for integration, for the integral of x to the power of n with respect to x. And that integral is equal to x to the power of n plus 1 instead of n minus 1, divided by n plus 1. And of course, plus c for the integration constant that we talked about in the previous video. But we'll do a few examples to apply this. Now, let's go back to definite integrals. We have the integral of any function from a to a. So that's when you have the same number for the integration limits. That's always going to be equal to 0. Imagine you have a plane with x and y. Now remember, the integral under this function, f of x, or y equals f of x, is just the area under it, okay, between the function and the x-axis. Between the boundaries a and b. But now if we have the boundaries being a and a, that's like taking a and b and making b go really close to a. And as you can see, all this area will be lost, and the area tends to 0. So that's the value that we assign to the definite integral as well. So whenever you have a number here and the same number here, then that definite integral will just be 0. Okay, next rule, if we have the integral from a to b of a function, then we can say that that's equal to the negative integral of that function with the boundaries flipped. So here we have from a to b. We can switch them around and say integral from b to a if we add a minus sign. Okay. And this minus sign is essentially just a factor of -1, right, times that integral. So it doesn't matter if we write this factor of -1 on the outside of the integral or if we move it inside, due to, or rather thanks to the first rule that we saw for definite integrals here, with bringing the constant out. And finally, if we have an integral from a to b of the function plus an integral from b to c of the function, then we can just rewrite this as the integral from a to c. And again, we can show it using areas. Imagine this is our function y equals to f of x. Doesn't matter what it is. But let's say a is here, b is here, and c is here. This first integral is the area under the function from a to b. So that's this area. And then this integral is the area under the function from b to c. So that's this area here. And we're saying that this is equal to this integral, which is the area under the function from a to c. There we go, from a to c. And that is indeed true. As you can see, we have all of this area shaded. So that's how we can sort of visually show that rule. Okay, let's move on to some exercises. The first one here asks us to prove the reverse power rule. Now, we aren't really going to prove it, we're just going to show that it's true, so this won't be a formal proof. And we can start out by writing the reverse power rule. So it says that the integral of x to the power of n dx is equal to x to the power of n plus 1 divided by n plus 1 plus c, the integration constant. So since we're trying to show that it's true, we can put a question mark on top since we're asking if it's true, and then we'll reach a statement which is true, and that's how we will show that it's been true, that it is true. So let's start by taking the derivative with respect to x of both sides. So the integral and the derivative on the left side will cancel out. So we're just left with x to the power of n. Is it true? Is it equal? Now to differentiate the left-hand side, let's start with this term, since we're differentiating term by term. We have a 1 over n plus 1 constant multiplier. Remember, it's with respect to x, so n is just a constant. And then we have x to the power of n plus 1. That's just a power, x to a power. So we can just use the power rule. We can multiply by the exponent n plus 1. And then we have x to the power of n plus 1, and then subtract 1 since we're differentiating. And then the constant differentiates to just 0. Right, the derivative of a constant is 0. So now we see the n plus 1 cancel out, and here the plus 1 and minus 1 cancel out. So we get that x to the power of n is equal to x to the power of n, and this is of course indeed true. And just like that, we've shown that the reverse power rule is correct by differentiating. Or actually, I'll leave this here. Okay, let's move on to the next exercise. Under what conditions is the power rule correct? This should be the reverse power rule. Reverse power rule. And to answer this question, we can just look at the power rule. You'll notice that there's a denominator of n plus 1. So, of course, n plus 1 cannot be 0, meaning that n cannot be minus 1. So, we cannot have, if we have the integral of x to the power of minus 1, which is the integral of 1 over x, right? Then we can't use the power rule for this, and we need another rule to integrate. And I haven't written the dx's here, but you should, okay? There we go. Let's move on to the next question. So, or technically to fully answer this, we can say n plus 1 is not 0, therefore n is not minus 1. Or we can say n has to belong to reals, excluding the element minus 1. Like that. Next, we have the integral of dx over x. So we can say this is just the integral of 1 over x dx. You're allowed to do that. So here they're just asking us, actually, what do you do when n is minus 1, right? This is the same case that we excluded previously. So obviously we can't use the power rule. What can we use instead? And we haven't seen this integral, but you can just guess which function differentiated gives 1 over x. And from the previous chapter on differentiation, you should know that this is just the natural logarithm function, and always add the integration constant when you have indefinite integrals. So the answer is ln x plus c. Next, we have the integral of e to the x dx. And again, we haven't seen this integral, but from differentiation, you should know which function differentiates to e to the power of x, and that is e to the power of x itself. So that's the answer, plus c. Okay, next we have a definite integral. E to the power of pi times x divided by pi to the power of e. Evaluated between minus 37 and 37. So instead of doing this the normal way for definite integrals, why don't we do it in two different ways so that you know how to do both? Now remember, e and pi are just constants, so their ratio is also a constant. So the function we have here is f of x equals to a constant times x. Right, that constant being e to the power of pi divided by pi to the power of e. And now if we sketch this, okay, we would have a straight line passing through the origin, y equals to f of x. Okay. And now I haven't made this the gradient accurate. That doesn't matter. All we need to know is that it's a straight line passing through the origin, and the boundaries are minus 37 and 37. And since we're evaluating areas, this area here is subtracted, and this area here is added, and they're equal in absolute value. so they will just cancel out, which means that the value of this integral is 0. And don't add plus c because it's a definite integral, okay? Definite integrals are just about what the area is, and the area is always a number. You don't have to add this plus c since we know exactly what it is. But we can also do this another way. We can first pull the constants outside of the integral, e to the power of pi divided by pi to the power of e. And now we just have x left over. We can use the reverse power rule. We have x to the power of 1. So when you integrate, remember we add 1 to the power, so we get x squared, and we divide by the power plus 1, so that's 2. So we get x squared over 2, but we use the square brackets because we have to evaluate this expression between minus 37 and 37, okay? So this is the alternative way of solving this integral. Okay, now we just substitute the boundaries. We have e to the power of pi divided by pi to the power of e. And then in brackets, we're going to have 37 squared over 2 minus negative 37 squared over 2. Okay. And now, hopefully, you can realize that this part is just equal to 0. We can remove this minus since it's squared. And then it's just one number minus itself, which is going to be 0. And since we're multiplying this constant by 0, the whole thing is also just equal to 0. So this is the more formal way of explaining why the value of this integral is 0, if you don't want to use a drawing. Next, let's move on to the integral of sine of x. So we can just, again, think about differentiation. Which function can we differentiate to get sine of x? And remember, sine and cosine differentiate to each other. So let's write that down. The derivative of sine of x equals to cosine of x, and the derivative of cosine of x equals to minus sine of x. So we want the derivative of something to be sine of x. Well, the derivative of cosine is minus sine of x. But what if we multiply both sides by minus 1? Okay, then on the right side, we just get sine of x. And on the left side, we get the derivative of minus cosine of x to be sine of x. So since we want to integrate sine of x, the value of that for the integral will be minus cosine of x. I'm just going to delete this and add the integration constant. Okay. Next, we have the integral of cosine of x. Again, think about differentiating trigonometric functions. If we take the derivative of sine of x, that's just cosine of x. So the answer to this question is just sine of x plus c. Okay,